Hello everyone, I am Roshan. I am one of the TAs for the Big Data and Biological Networks course, and in this tutorial session we will be seeing how to implement node embedding methods using Python. So we will start by importing some essential packages. We will be using matplotlib and cbond for plotting, networkx to deal with the graphs, numpy and scipy to perform linear algebra operations, pandas for reading data sets, and we will be also using two packages. One is called gensim, which we will be using to implement the word-to-vec model for random walk based methods, and then we will be using another package called karate club, which has built-in methods to make our life easier, and we will also be using the scikit-learn package to implement machine learning models. I will start by importing the packages. Yeah. So what do I mean by node embedding? If you recall, we have a graph, and for each node in the graph, we will be getting the corresponding embedding here. And this graph is from something called the Zachary's Karate Club, where each person here represents a node, and there is an edge between two nodes. So as you can see here, each node has an embedding in this embedding space here. So these are two-dimensional embeddings, and the embeddings are close if they are also adjacent in the graph. So this is our objective. Given a graph, we will get an embedding for each node, and the embedding should also determine capture the statistics or structure of the graph given as input. So we will be using the networkx package to read something called the edge list. In this tutorial, we will be using the human disease network as our data set. So we will be reading the edge list. So edge list where each entry or each row corresponds to an edge, and each edge is represented by two node IDs. So if both the node IDs are present in the edge list, they have an edge between them. So we will be using the networkx package to read the edge list, get the list of nodes, get the list of edges, and we have to predetermine, we have to define something called the embedding dimension here beforehand. So I will be assigning that to 128. So if I read it, so this is your edge list where you have two node IDs, and these are the list of nodes. So okay. And this is the representative network of the human disease network. So where each node belongs to something called a disease class. The node here can be belonging to the neurological class of diseases. This node might be belonging to the immunological class. So and as you can see, the network is quite visibly clustered corresponding to different disease labels. So and what the objective here is, given the graph and the node ID, we have to get an embedding, and based on the embedding we have to predict the disease class. And if you recall from the previous lectures, there were two main paradigms to get node embedding. So one is the matrix factorization based approach, and the other one is the random walk approach. We will be going into detail on both the approaches, and we will be starting with Laplacian eigenmaps, which is a matrix factorization based approach. So Laplacian eigenmaps, these are the steps involved in the algorithm. We will first start by computing the Laplacian matrix. So that is just the difference between the degree matrix and the adjacency matrix. I will be getting the Laplacian matrix here, and there is also a convenient function in networkx called the nx.Laplacian matrix if you do not want to write these boilerplate code. So I got the Laplacian matrix here, and so after getting the Laplacian matrix, we will be solving something called the generalized eigenvalue problem. So in the typical eigenvalue problem, you won't have this D matrix. So this will be the identity matrix, and in the generalized eigenvalue problem, the eigenvalues and the eigenvectors depends here on the matrix D. So we will be solving the generalized eigenvalue problem, sort the eigenvectors according to the corresponding eigenvalues, and so we will be leaving out the first vector corresponding to the eigenvalue of 0, and we will be taking out the top k eigenvectors, the k being the embedding size. So there is the eigenh function in SciPy, and that helps us solve the generalized eigenvalue problem. We will be getting the corresponding eigenvalues and the eigenvectors, and to get the Laplacian eigenmap embedding, so we will be taking the first n components, leaving out the first eigenvector, since the eigenvalue is 0 corresponding to the first eigenvector, and we will not be doing the sorting here. SciPy automatically takes care of it. So you got the Laplacian eigenmap embeddings here. You will be seeing it. See, this is basically your array. If you see the shape of it, you have 516 nodes, and each node has a vector of size 128. So, and the next method that we will be looking into is called the inner product method. Here we have to define something called the similarity measure. In the very simplest case, we can take the similarity measure to be just be the adjacency matrix, and we will be doing low dimensional factorization of the similarity measure using something called the truncated SVD. So we have the similarity measure matrix here. We will be decomposing it into the corresponding U, D and V matrices using SVD, and we will also be only taking the top k or d components corresponding to based on the sorted eigenvalues, and so we will be using the randomized SVD function again from SciPy, and we will be specifying the matrix similarity measure or the matrix adjacency matrix here, that is A, specify the number of components to take and the random state, because these are approximation algorithms and we want it to be deterministic, returning the same value every time we run it. So after getting these three matrices, we will be doing just the dot product of the similarity measure and the V matrix to get the inner product embeddings. I will just be running it here. So these are our embeddings. Again, the shape will be the number of nodes in the first dimension and the embedding size. So these are the two main matrix factorization methods. Now we will be moving into the random walk based approach, starting with DeepWalk. So in DeepWalk, again we have the graph as input. We get the node embedding based on the weight vector, and we will be performing an operation called hierarchical softmax to speed up our computation. We will be going through it step by step now. To implement the DeepWalk algorithm, I will be implementing the random walk function. The arguments here are the starting node, the walk length, the length of the random walk, and I will be setting a seed for reproducibility. So before I start my walk, I will append my starting node to the walk list, and from the starting node I will be looking into all my neighboring nodes, and based on the random chance I will be picking out my next neighbor, moving to the randomly selected node. I will be appending the next node to my random walk list, and the next node will become my starting node. So this is how the random walk function is implemented, and here I have let's see a sample output. As you can see, this is the random walk of length 10 being implemented. So yeah, and for the DeepWalk approach, we will be doing this based on the number of random walks we want, and so we will be repeating if the walk number is 5, we will be repeating it 5 times for all the nodes in the graph. And to do it in a simpler way, as I told you before, Karate Club makes our life easier by already having a class that can implement these random walks. So I have set the walk length to 5 for each node. Give me a random walk of size 5, and for each node repeat it 5 times. So this will do all the walks for the graph, and the walks attribute contains my DeepWalks. See, I get an entry. Each entry in the list has size 5, and so the total number of walks will be the number of vertices times the walk number. So these are my DeepWalks. Yeah. So after getting these random walks, we'll be implementing something called the word-to-vec model. So there are two main approaches used in the word-to-vec model. So one is called the continuous bag of words, CBOW, or the scriptgram model. So these are the representations of how continuous bag of words and scriptgram works. And so we have something called the input, where the input corresponds to the node IDs. So we'll be modeling these random walks as natural language. So given a node, we'll be getting all the surrounding nodes based on something called the window size, and based on the embeddings of the surrounding nodes, we will be getting those individual embeddings, summing it all up, and we will be predicting what will be the current node. So based on the surrounding nodes, I will be predicting the current node. So this is how continuous bag of words work, and skipgram is quite totally the opposite. Given my current node ID, I will be predicting what will be my neighbors. So this is kind of like the inverse problem that we'll be doing here. So to again make our life easier, we'll be having something called word to ID and ID to word variables, where I'll be mapping each node to an integer, and so again I have to map my integer back to the node ID. So I'll be having two variables here. So let's see how it is. So node ID 340 corresponds to an integer value of 0, and as we go through this tutorial, you will understand why do we need it. So this is basically how the skipgram model works. We have an input word, and the surrounding words are my context, and so how do we generate the training data for this? So each pair of the input word and the context word become my training data set. So as you can see here, this is my training data set, and this will be repeated for each and every word in the text, or in our case for each and every node in the graph. So how do I represent it to the word-to-vec model? I will be using the one-hot encoding, and it will be taking in two arguments, the token ID and the vocabulary size. So what will be the vocabulary size? That will be the total number of nodes in the graph, and if suppose let's say node 340 is present and the corresponding ID for the node is 0, we will have a vector of size 516, and the 0th element will have the value as 1, and the rest all will be 0. So this is how the one-hot encoding works, and I will be using a function called generate data to generate my training data set. So we have to give in the list of random walks, we have to set the window size. So window size here basically determines the amount of training data that you have, or the amount of context you can capture. So here the window size is 3. So based on my input word, I will be taking in the previous 3 nodes or tokens here, and I will also be taking into account the next 3 words from the input. So this is basically the window size, and I will also be giving in the walk length. So for each node in the random walk, I will be looking at let's say the window size is 3, I will be looking into my 3 previous neighbors and the next 3 neighbors, and I will be creating the training data set, and I will also be using the one-hot encoding. So X has the training data and Y is my corresponding label here. I will be running this function. So let's generate this, As you can see, we have around 46,000 training data points, and we have it for each of the so 516 is my vocabulary size or the number of nodes.